Hello class, this is section 2.4 and in this video we are going to talk about the insulated boundaries problem with Fourier series. So we have this heat equation problem again for a rod in one dimension, but this time rather than having the temperature at the ends of the rod set to 0, we are saying that the rod has insulated ends, so no heat changes at the ends of the rod. This is represented by having the partial derivative with respect to x 0 for both sides and with an initial condition. So again, we want to determine what the product solutions are first. uxt equals fxgt. And once more, plugging this in to the heat equation gives us two ordinary differential equations. The one with respect to t, which is going to be 1 over gt partial gt partial t equals minus lambda, with a k here, of course, and one with 1 over fx partial squared fx partial x squared equals minus lambda as well. The G equation works the same as it did before, and using the separation of variables argument, we can find that this gets us gt equals e minus lambda k t, again with the constant c set equal to 1 just for convenience. The eigenvalue problem for the f is a little different though, because our initial conditions have changed. This time we have that the partial of f x partial x partial of x set to 0 equals 0, and partial of f with respect to x set to L equals 0. So we have to solve this eigenvalue problem instead, and using the techniques you learned in ordinary differential equations, you will find that the eigenvalues are lambda equals 0 and lambda equals n pi over L squared once more for n equals 1, 2, and so on. So remember that we have a 0 term unlike the previous case. The eigensolutions, the eigenfunctions are a bit different. So eigenfunction for lambda equals 0 is just going to be 1, and the eigenfunction for lambda equals n pi over L squared is cosine this time, n pi x over L. And this makes things a little bit different, but fortunately all the techniques, all the formulae for Fourier's theorem still work for cosine as well as sine. And this means that we have product solutions of the form un xt equals e, so minus lambda, so lambda here can be written in the form minus n pi over L squared kt times sine n pi x over L. Sorry, I mean cosine this time. So these are our product solutions. And again, if our initial condition fx were a sum of cosines of this form, we would be done, but we need to be able to express an arbitrary function in terms of cosines. But we also have a Fourier theorem for cosines, and it works more or less the same way. We have fx can be written down in terms of b naught plus the sum from m equals 1 to infinity bm cosine m pi x over L. So nothing very much changes with the expression. Now we have to think a little bit about how to write down the Bm, how to find the Bm terms, the constants. It turns out that for m not equal to 0, everything works the same way as the sine case. In fact, we get exactly the same formula. So we have that Bm equals 2 over L integral from 0 to L fx cosine m pi x over L dx. The only headache is that we have this b naught term, which we have to handle a little bit differently. But it's not too hard to figure out what b naught should be. What we do is that we take the Fourier's theorem. Let's say, okay, for m equals 0, let's do this. We take the Fourier's theorem, we multiply, we integrate it from fx dx, and see what happens, from 0 to L, of course. And we end up with integral 0 to L b naught plus sum m equals 1 infinity bm cosine m pi x over L dx. Okay, and so the first term just becomes a b naught x from 0 to L, and then we have all these cosine terms to integrate to. It's not too difficult to see that all of these cosine terms, when you integrate them, go to 0. So these are all equal to 0. And we just left with b naught times L. So in fact we have b naught equals 1 over L integral of 0 to L of x dx. If you don't see why all these terms go to 0, I encourage you to take the time to calculate this integral. It's not very hard, and you'll get that for every n other than 0, you get the integral of this cosine being set equal to 0. But anyway, you get a b naught equals 1 over L integral of fx dx. This is the only difference really with the sine case.